Okay, well, welcome to the additional 7 people. We're just going to see if anybody else turns up just for a minute or so more. Okay, just got rid of my unwelcome co-host, so we're ready to start. So it's week 8, intro to statistics. Welcome everybody and good afternoon. Lovely to see everybody in the chat. Hey. I hope you had a nice break and that you feel a little bit like you caught up. And I'm going to crack on now that I'm doing anything weird in the background. Okay, so I've decided to do question 2, question 4 and question 6 from sheet number 8. And on Tuesday morning, we managed to get through all of them just about. So hopefully with the extra few minutes we've spent waiting for people to arrive, we'll still be okay to get to the end of this. Okay. I've also got a little bit of a cold. I think it's some hay fever, so excuse me if I start sneezing all over the place. Right, let's crack on. We'll start off with question 2. Question 2, we were given a couple of different things. Let's look at the question again. Yeah, we were given the sample means of 2 independent samples, x1 and x2, and you can just about see the little, oh, okay, we've got more people arriving, so I'll let them in as well. Oh dear. Anyway, all right, so we've been given two sample means, x1 and x2. And we know that these are from samples of size n1 and n2 respectively. And what we've been asked is we've been told that sigma, so the variance is known, and the mean of this underlying data is unknown. And we've been told if we use a estimator for the mean, which is a mix of these 2 sample means, we've been asked to calculate some properties of that. So the estimator we've been given is mu hat, and it's alpha times x1 bar plus 1 minus alpha x2 bar And the first thing we've been asked to calculate is the bias. So the bias of new hat is going to be the difference between the expected value of new hat and the actual value of the population mean, mu. And this is not too bad to calculate if we can remember some of the features of x1 and x2 bar that we've got here. So what we need to remember is that because they're sample means, x1 bar is going to be normally distributed with mean, the same as the population mean, and with variance, which is going to be sigma divided by sigma squared, sorry, divided by n1, because we've got n1 elements in the sample. So with that in mind, have a think about what the distribution of x bar 2 would look like, and see if you can work out this one. Maybe just insert the definition and use some of the properties of the expectation. So I'll just give you maybe 2 minutes or so just to look at that, and then we'll start working through it together. I've left somebody waiting outside. So welcome to the 2 extra people. We haven't really got very far yet. We're still looking at the first question that I've decided to look at, which is question 2. At the moment, we are having a little go at calculating the bias of new hat, and you can see on my working out that we calculate that as the difference between the expectation of new hat and mu. We've got a formula for mu hat there, and I've reminded everybody that the distribution of x bar 1 is going to be normal with parameters mu and sigma squared divided by n1. So yes, Pedro, we are assuming that the population mean is the same for both samples. So I think the phrasing of the question was such that we were taking 2 samples from the same. Okay, yeah. So I'm not so sure about 113 because I've not actually prepared the answers to all of the questions. I think we should maybe stick to the other ones, Joe. But the solutions are nice and clear. So by the end of today, you should have the solutions, and you should be able to run through what's there. Okay, so let's just crack on. So if I insert the definition of what mu hat is, I'm going to have the expectation alpha x bar 1 plus 1 minus alpha x bar 2. Now I can use linearity of expectations. I can take, it's an expectation plus an expectation, and I can also take the constants out as well. Now, hopefully, you guys are happy with the notion that the expectation of x bar 1 is mu, and the expectation of x bar 2 is also going to be mu. So we're going to have alpha mu, 1 minus alpha mu, and minus mu, and altogether that's going to be 0. Okay. So next, let's have a look at the variance of mu hat. So we're asked, what's the variance of mu hat? And I think the first thing you want to do there is you want to do something very similar to what you did before. You want to insert the definition of mu hat here, and you want to use linearity and maybe another rule that you know about variances to get a little bit further with that. We were then asked to try and find the value of alpha such that the variance is minimized. So I'll give you a little bit of time to think about that one as well. You're going to need a second order condition as well as the first order condition, but just work on the first order condition if you have time for now, and we'll go forward from that point. And I'll give you maybe close to 5 minutes to have a little think about it. Okay, so let's crack on. So I think the first thing you're going to want to do is insert the definition of new hat. In here, I can have it as the variance of x1 plus the variance of x2. And if I've got a constant, I can take that outside the variance and square it. So I'm going to have alpha squared variance of x bar 1 and 1 minus alpha, the variance of x bar 2. And then from there, I just need to have a think about that distribution that I was given. So this one here, so I know the variance of x bar 1 is sigma squared divided by n1, and the variance of x2 is going to be similar as well. Yeah, I missed out off the square. Thank you so much, Pedro, and Camille as well, yeah. Fantastic. See, you're spotting all of my errors, which is really good stuff. So sigma squared divided by n1 and 1 minus alpha squared, sigma squared divided by n2. Okay. And then if we wanted to try and minimize this, we're going to want to try and find a point where the derivative is 0. So hopefully you all had that in mind when we were looking for a minimum, is the variance of new hat with respect to alpha needs to be equal to 0. Now, if I differentiate the first term, I'm going to end up with 2 alpha and then a constant again. Okay, now with the second one, certainly you can just expand it out and then differentiate. So I'm going to have an alpha squared term and a minus 2 alpha term as well. So I'm going to end up with plus 2 alpha minus 2 sigma squared divided by n1, n2, sorry. And all of this I'm going to need to set to 0. So now that I've got it set to 0, I can cancel some terms. I can cancel the 2's because there's lots and lots of 2's, and I can cancel the sigma squared as well because that's in both terms. If I then rearrange that, I'm going to get the form of alpha that was given in the question. So okay, right. And I would also need to check the second order condition as well, because if I've just set the derivative equal to 0, this could be a minimum or a maximum or a saddle point or whatever. So make sure you check your second order condition as well. Okay, so while you were taking a go at that, I looked at the question that Joe had as well about the sampling distribution of an estimator, like in part 3. And what I would like to point out there is you have in the previous part of the question, in question 1, part 2, you calculated some sample you calculated the variance of the estimators. So you calculated variance of mu hat 1 and the variance of mu hat 2. Now, because you know that the sampling distribution of the mean, you know that so you should know in both cases that because it's combinations of mean of different samples, which looks quite like a mean, that hopefully it's going to be normally distributed with the parameters that you found part 1 and 2. And then from those, you can deduce what the actual variances are, because you would be hoping that, for example, if you know what this one is, then you've got something like this. Is normally distributed with parameters, some like mu hat 1. So expectation of mu hat 1. And the variance of mu hat 1. And because it's related to sample means, what you're the position that you're in is that you know that this term here should in principle be sigma squared divided by the number of elements in this overall. So we should know that that one should be divided by anyway, no, I'm confusing myself now, but yeah, exactly. That's why I shouldn't look at things live. But essentially, the third part is a one-liner, which is based off your answers to part 2 and part 1. So that explains why I shouldn't look at things live. Moving on. Let's try and end up somewhere slightly more confident. So, a completely different tutorial. And Joe says it's fine, even though I've got a bit confused as to what I'm doing there. So hopefully he's sort of been able to guess what to do next from what I said. So yeah. Okay. Question 4. what we got with question 4. So with question 4, we were told that we've got 5 elements, and it's a random sample from a binomial distribution. And we know that there's 3 possible outcomes, but we don't know what the probability P is. So each of the little xi's can take can take any of the following values. So it can take 0, and then 1, 2, or 3. Yeah. And the likelihood function, we've been asked in the first case for the likelihood function, and then to find out based on that which of the possible values of P is most likely. So where we want to start with the likelihood function is that it would need to be a product. Needs to be a product, and then here needs to go the probability that the random variable from this. So if X is distributed according to the distribution we've been given, according to binomial 3P, what we need to put here is the probability that X equals the little xi that we've observed. And you should know what the distribution function for the binomial distribution is. So we're fine. We can insert there. So 3 choose xi, and then pxi, and 1 minus p raised to the power of 3 minus xi. Okay, so it's fine if you wanted to just leave it at that, but you can make it slightly more simple. And the reason why you can make it slightly more simple is that you've got a term which is pi in each of these terms, and you've got a term that is 1 minus p to the power of something in each of these terms. So we could group all of these together. So first of all, I'm just going to split them out. So if you're thinking, if I'm multiplying terms together and each term is made up of 3 things multiplied together, I can just multiply all of the first terms together, all of the second terms together, and all of the third terms together. So first thing I'm going to do is just switch to multiplying all of the choose terms together, all of the p terms together, and all of the 1 minus p terms together. Okay. Now I can't really do anything about simplifying that first one, so I'm going to leave that one as it is. But the second term I can do something about. So what am I going to have? I'm going to have pxi, px1, px2, px3. So I can switch this one to p raised to the power of the sum of the xi's. And the same with this one. I can change the product here to a sum of these terms here. And hopefully you're happy with the fact that if I'm summing up 3 lots of 5, I'm going to have 15, and then the sum of the xi's there as well. So we can even make that term one term simpler as well. So that's given us an answer to part A. So part B, the first thing I want to be doing there is I want to be finding LP in the particular case that I've been given. So the data we've got is x1 is equal to 1, x2 is equal to 3, x3 is equal to 2, x4 is equal to 2, x5 has the value 3. So given that information, we can simplify our expression for L a little bit. Okay, so we can get those values of xi in there for, and then the only thing that we don't know in LP is going to be P. And then from there, we're going to be able to populate a little table. So the possible values of P that we've been given are 0 0.5, 0 0.6, 0 0.7, 0 0.8. And I'm going to want to calculate LP in each case. So see what you can do with those, and yeah, just give it a crack. So simplify LP a bit just to make your life a little bit easier. And then get calculating LP for those 4 values. And if you can find the biggest one, because we're going to be looking for the biggest one to maximize the likelihood function, just post in the chat or direct message me which one you think is the biggest of those 4. And I'm going to give you about 7 minutes or so to give it a go, so that we'll be around about 35 minutes past, with 10 minutes to talk about the answer and talk about question 6 as well. If anybody's got anything else they'd like to ask, either in the chat or direct message, like, feel free. So nobody's sent me an answer yet, so I assume you're all busily working away. So they're all pretty poxy and small. I've got one person who's sent me the right one. Two people who've sent me the right one. I think one person who might have made a tiny little error in the calculation, but let's just crack on and see what we get. Like, I'm sort of glad that you managed to give it a really good solid go. So the first thing I would say is if we add all of these up, we're going to get to 11. So we can quite clearly see there are 11. So I'm going to be able to put 11 here and 15 minus 11 here. Okay, and then it's a question of what that constant is. So these terms here. Now, when I've got x1 is equal to 1, 3, choose 1, 3, right? 3, choose 3, 1. And 3, choose 2, 3 again. So if I multiply all of those together, I'm going to have 3 times 1 times 3 times 3 times 1, 27. So I'm in this position. I've got 27, P11, 1 minus P to the power of 4. All of these numbers are really, really tiny, but the right one is 0.7, which has a value of 4.32 times 10 to the power of minus 3. So they're all pretty kind of dinky. Okay, but at least you were all going in the right direction. So let's have a look at question number 6 as well in the final 10 minutes that we've got. So in question 6, we were asked for 2 confidence intervals. We were asked for a 95% confidence interval and a 99% confidence interval. We were given a sample. It's got 10 values in it. So we've got n is equal to 10. And we were given what sigma was as well. That was going to be 0.8. It's assumed to be known. And we were asked, what's the 95% confidence interval for the mean of this data? So the first thing we need is we need to know what the mean so we need to know what the mean of the sample is, so that we can then have a 95% confidence interval for the actual mean. So if we just take each of the values in the sample and calculate the mean of those. I'm going to call it little x bar because it's a mean. You should be able to crank that out from the 10 data points that you've been given as 11.48. So that's going to be in the middle of our confidence interval. So our 95% confidence interval is going to be some kind of range. It's going to have 11.48 in the middle, and then it's going to have something on this end and something on this end. So the probability of being outside past my question mark on this side is 2.5%. And over here is 2.5%. Now, that was a mistake that I'm sure I made at least once as an undergraduate myself, is like just putting 5% on each end of the distribution and being like, well, that's right. And actually, I just made myself a 90% confidence interval rather than a 95% confidence interval. So what we need to do is we need to find a value of Z. So a possible value of that item in my sample that goes either here or here, such that we've only got 2.5% stray at the side there. So the Z that we're looking for is going to solve if I stick it into the CDF of the normal distribution, I'm going to get that Z back itself. Now I'm going to want to index my Z by something because I would like to be able to distinguish between this part and the second part of the question. So what I'm going to do is I'm going to set alpha equal to 0.05, so the 5% that I don't want in my confidence interval. And then what I'm going to be interested in is I'm going to be interested in putting the index on my Z of 1 minus alpha divided by 2. And that's just going to stop me from accidentally putting all of the weight on one side. So remember, it's divided by 2, and it's only the alpha that's divided by 2, not the 1 as well. 1 minus alpha divided by 2 here. 1 minus alpha divided by 2 here. So it's a value such that, there you go, it's a value. Z is a value such that when I put it into the CDF of the normal distribution, the value that I get back is the value of its index, so 1 minus alpha divided by 2. So in this case, what I'm looking for is I'm looking for a value of Z, so that when I put it in the CDF of the normal distribution, I'm going to get out 0.9725. Okay, 975. Okay, 0.975. So that's what I'm looking for. I'm looking for a Z such that that applies. 975. And I can look that up in my table. So I can find Z from the table. And it is 1.96. Okay. With that in mind, I can then decide what the ends of the confidence interval are using this. So the value, I need to do something to my Z in order to put it at this end of the confidence interval. I need to rescale it correctly with the sample mean and the variance. So I'm going to need to put Z here. So this value here, this question mark, is going to be X bar plus Z 0.975. Now that's the X bar there is to center in the right place. And then if my X bar was normally distributed with parameter with variance 1, of course I could just leave it as Z there, but I've got to standardize it as well. So how I'm going to standardize it is multiplying by sigma and dividing by the square root, so dividing by square root of 10 as well. So the interval that I'm going to have overall is going to take exactly that form. Okay, so I'm going to have 11.49 minus 1.96 times 0.8 divided by square root of 10 as the bottom value, and then at the top value, very, very similar. So plus here, 1.96 times 0.8 divided by square root of 10. Okay. Now, we've got 3 minutes left. Oh, just thanks, Joe, for pointing out that I need to just not ramble and make sure that you can always see what I'm working on. There's our 95% confidence interval. So if I wanted to change it to a 99% confidence interval, there's only one thing I really need to change, and it's that value of Z that I'm putting in. I need to change what the number is here, and resolve this equation for a new value here. So why don't you give that a go for the final 2 minutes? Just have a think about what kind of value you're going to be looking up in the normal distribution table, and whether you expect this, what you expect to really happen to the values of this confidence interval. And other than that, I'll see you guys in a fortnight for more statistics. Hey, so fun.
Sorry, in the confidence interval, where do you get the 0.8 and the root 10 from?
Okay, so the 0.8 is from the question. We were given sigma is equal to 0.8 in the question, and the root 10 is because there was 10 elements in our sample.
Okay, thank you.
So yeah, effectively the variance, the variance of the sample mean would have would be 0.8 squared divided by 10, which is why when I'm trying to multiply by the standard deviation, I need to multiply by the square root. Is that right?
Yeah, that makes sense. Thank you.
Fantastic. Is there anybody else who'd like to ask anything? I'm more than happy to try and address any concerns that you've got about those 3 questions. Well, I think I'm going to grab a snack while I'm waiting for the next class. I'm so hungry. I only ate my dinner just like 15 minutes before the start of the previous class. Yeah, that's not a good time to be having your lunch. Like, Okay, so thank you everybody who's here already for being early for the 5 o'clock class. I'm going to wait until 5 or maybe 2 minutes past 5 or something like that for everybody else to turn up, obviously. Today it's sheet 8 of Intro to Statistics, so we're only like 3 weeks away from the end, which is really good. So what I'm going to look at is question 2, question 4 and question 6. So if you want to take a look at your answers to those, if you've worked on the sheet in advance, or start working on them so that you feel a little bit ahead by the time that we start talking about them, feel free. If you've got a question about one of the other questions, 1, 3, 5 or 7, throw it out there now and I will try and look at it in the next 5 minutes or so and see if I can say something intelligent about it. Somebody asked me a question about question 1, part 3. In the previous session, so I might reiterate that as well slightly more clearly than I did last time. Fun. Yeah, so otherwise just relax and enjoy. 5 minutes spare until everybody else turns up, all those lazy ones. No, I'm sure they're not. I'm sure they're just very busy. So you might be able to hear a small person in the background. This week she's figured out that if you put her down and she screams loudly enough, that you pick her back up again. This is bad. It basically means that if you're on baby duty, you can't do anything. You put her down to like go to the bathroom and she screams. So I'm going to continue waiting some extra people. But as I said before, if you want to just write in the chat anything in particular that you want an answer to, or you can turn your mic on and just say like, oh, come on, do question 5. You know, feel free. My plan is to not do question 5. My plan is to do question 2, 4 and 6. But feel free to ask about anything you need to. Okay, one more person waiting. I'm hoping I'm going to have a flood of extra people around about like 2 minutes past as I did an hour ago, because that makes me feel even better. Don't watch the clock behind my head for the time because it is wrong by 5 minutes so that you never miss the train. Instead, obviously, look at the one in the header.
Good evening.
Evening. Okay, so just a couple of minutes more just to make sure we've got everybody we can. Okay, so I'm sure a few more people will drop in sometime in the next 5 minutes, and that is of course fine. So I'll start off moderately slowly. It's intro to statistics, week number 8. Oh my goodness me, there's only 3 more to go, isn't it great? And I hope you have had a really, really good couple of weeks break. I did, it was lovely. We've got one more person waiting. So this week, it's just loads more stuff about estimators and confidence intervals and stuff like that. I've picked out 3 questions to give a go. Question 2, question 4, and question 6. Just because they're on really different things. So question 1 is about doing some calculations with a potential estimator. 3 more people waiting, so I was right to start off a little bit slow. So yeah, question 2 is about calculating some properties of an estimator. We're going to give that one a go. We're going to give question 4 a go because we get to write down the definition of a particular likelihood function, try and calculate a maximum manually. It's quite interesting. We'll probably try and squeeze in question 6 as well because we've got a confidence interval in there. And I might actually present it significantly better than I have done in the previous 2 classes because I thought, oh, this is so easy. And then just started talking and just gobbledygook came out. So I'm really hoping that question 6 goes better for me, but it's not too difficult. So hopefully, even if I start falling over myself, you guys all know what you're doing. Fingers crossed. So let's all start with question 2. Yes, we switch to the visualizer. And as I said before, excuse the background noise. I've turned off Sarah Lisa's background noise, but I can't really turn off my own. Okay, here we go. Right. Right, so hopefully you can all see the visualizer. All right. I found the focus button on it about a week ago, so I'm much more happy with the visualizer than I have been in the past. So question number 2. We were given 2 sample means, x1 and x2, and they're from the same underlying distribution. And we've been told that we know what sigma is, but we don't know what mu is. So they're sample means of sample sizes. N1 and N2 from the same underlying distribution. We know sigma. And we know that because they're coming from the same distribution, sigma is the same in both cases. Yeah, sigma is the same in both cases, coming from the same underlying distribution, but we don't know what the mean of the underlying distribution is. Unknown is the mean of the underlying distribution. And what we've been asked to do is we've been asked to consider a particular estimator and to find the bias and the variance, and then to find a value for alpha such that the variance is minimized. So the estimator we were given is mu hat, which is alpha times x bar 1 plus 1 minus alpha x bar 2. Okay, so I guess the question really is, if we have 2 samples of different sizes, so say I took a sample of size 100 and another sample of size 10 from the same underlying distribution, which one should I trust more? Should I put more weight in the mean that I derive from a bigger sample, or should I put and how should I kind of mix those 2 together? So that's sort of where the underlying idea for this question comes from. So I was given this particular form from mu hat, and everything should be moderately easy to calculate if we can remember something about the distribution of the sample mean. So what I'll give you one of them. So the x bar 1 is going to be normally distributed with parameters mu, the same as the underlying population. Don't know what it is, no idea what it is. And then variance is going to be sigma squared divided by n1. So I'm expecting the variance of x1, x bar 1. So if I took lots and lots of different samples of size size n1, I'd expect their variance to be sigma squared divided by n1. So with that in mind, we've been asked to find the bias of new hat, which is the difference between the expectation of mu hat and the actual value of mu. So the expected value of our estimator minus the actual mean. And hopefully you can give that a little bit of a go. So I'm going to give you maybe a minute or 2. Let's go for about 3 minutes to give that a little crack. And just check that you can show that it's equal to 0. If you've done it already, or you think it's like not worthy of, takes shorter than 3 minutes, just crack on with the rest of the question, and I'm sure we'll catch you up sooner or later. Okay, so hopefully you were all okay here. Hopefully you could just write this expression into the expectation and take some things out. So you'd have the expectation of alpha times x bar 1 plus 1 minus alpha x bar 2, needed to subtract off mu as well. So the first thing I can note is that expectations are linear, so I can take the expectation of the first term and add on the expectation of the second term. And I can also take the constants outside as well, so I can move the alpha outside the expectation because the alpha is not a random variable, just x bar 1 and x bar 2 are random variables. Okay, now hopefully at this point, the fact that I gave you this clue is kind of helpful, because if x bar 1 is normally distributed with these parameters, then the expectation of x bar 1 is going to be the mean there in the normal distribution. And similarly with x bar 2, I'm going to have to think, well, what's the distribution of x bar 2 going to be? It's going to be very similar. Okay. So again, expectation of x bar 2 is going to be mu. Again, it's something that we don't know, but plugging those in, I'm going to have alpha mu plus 1 minus alpha mu minus mu. And hopefully you can immediately see that those are all going to cancel out. This one cancels with this one, and the 1 here cancels here. We've got 0. So fantastic. We've got ourselves an unbiased estimator. That's pretty nice. So for the second one, we've been asked, first of all, find the variance of mu hat. So hopefully you can use your rules about the variance to do something very similar there. And it's then asked us to find a value for of alpha that minimizes the variance. And I would propose you maybe start on that as well. I think I'll just leave you to give that a little bit of a go. We've got one more person waiting, so just let them in as well. So I'm going to give you, I think, 3-4 minutes just to give the variance a go, and also to give trying to minimize the variance with respect to alpha as well. Sorry. So welcome to the 3 extra people that just joined us. We're just taking a look at question 2. So if you want to jump right in with us, take a look what is already on my visualizer and see if you can take a go at calculating the variance of mu hat and minimizing it with respect to alpha. I've asked you to do 2 steps there, so if you just get a value for the variance of mu hat, that's probably sufficient at this stage. Okay. Yeah, I think I pretty much feel like that as well. Like, yeah. So calculating the variance of new hat, we've got something linear again. And we've also got some constants in there. When we take the constants outside of the variance expression, we always have to square them. So I'm going to be able to write here the x alpha squared, the variance of x bar 1, and 1 minus alpha squared, the variance of x bar 2. And then hopefully then you're fine, because you can just look at the expressions that we've got, because we know what the distribution of the sample mean is in relation to the distribution, underlying distribution. So we've got our N1 and N2 and our sample variances in there as well. So I can just write this expression, alpha squared sigma squared divided by N1, and 1 minus alpha squared sigma squared divided by N2. Okay, now if I wanted to try and minimize this expression with respect to alpha, the first thing I'm going to want to do is to differentiate it and set it equal to 0. And then that's going to give me a potential candidate. And then I'm going to need to check my second order condition just to make sure that I'm definitely looking at a minimum. So the first thing I want to do, calculate the derivative with respect to alpha of the variance new hat. So what am I going to have there? So this first term is going to be nice and straightforward. I've got an alpha squared times a constant. So the constant is going to be the same. I'm going to have 2 alpha. And then for the second term, I could do it by the chain rule, but I can also potentially just multiply it out. I think probably just multiplying it out is nicer. I'm going to have 2 alpha minus 2 sigma squared divided by n2. Okay, now for this to be minima, or for me to have a 0 of this expression, just let's set it to 0. Let's hope that at that point where the differential is 0 is equal to a minimum, not a maximum or a saddle point. But then we'll just double check. So there's some things I can cancel, right? I've got a sigma square in both terms. And I've also got 2 in both terms. I can get rid of all of the 2's as well. Okay, and then if I multiply both sides by n1 and by n2 and rearrange alpha n2 plus alpha minus 1, 0. Okay, and if I just divide through by the constant n1 plus n2, I'm going to get the answer that was given to me in the question, the possible candidate that was given to me in the question. And then to check that that is definitely a minimum, check the second order condition. Okay, so make sure you check your second order term to make sure that you're definitely at a minimum point. So moving on to question 4. With question 4, what I was given a random sample of 5 elements from a binomial distribution with parameters 3 and p. Okay. P, we don't know what it is. So guessing what P is going to be our approach. So each of these possible little x's can take any value inside this distribution. So for example, x, just any of those little x's, xi, is going to be one of the following values. It's going to be 0, 1, 2, or 3, because we've got a 3 in our binomial distribution there. So it's three total trials. So the possible number of successes range from 0 to 3. And then the likelihood function, hopefully you can remember, is the product the probability that a random variable capital X equals xi, and then if we define X to be distributed binomially, parameters 3 and P, like this. So we should know how to calculate what the expression for those probabilities is. Hopefully you remember it from probability 1, and hopefully you've been using it lots in this course as well. So hopefully we can, just jump in with that expression. So I'm going to have 3, choose xi, and then p raised to the power of xi, and 1 minus p raised to the power of 3 minus xi. Yeah. Okay. Now you could just leave that expression at that, and that would be totally fine. Might come to be a bit cumbersome to deal with in part B. So I'm going to expand on it just a little bit, but just be aware that if you just left it at that point, everything's cool. Okay, so the first thing I'm going to think about is with the product, what I'm being told is I'm being told to multiply terms of this type together. And the terms, each individual term is also a product of 3 elements. So there's nothing stopping me from multiplying each of the first elements together as a group, and then separately multiplying all of the p terms together, and then separately multiplying all of the 1 minus p terms together. So first of all, I'll start with doing that. So that first term, I don't think I've got much chance of simplifying that. So I'm just going to leave it at the beginning as a constant. And then I'm going to multiply all of my p terms together. And then multiply all of my 1 minus p terms together. Okay. Now, what I want to recognize in these 2 second terms is that because p is the same in each of the terms that I'm multiplying together, I can just add up the xi's. So I can swap the product of p to the power of xi for p to the power of the sum of the xi's. And you've got a little theorem about that Sally showed you, like pretty much in the preamble material before week 1. Okay, so I can swap that in that way. And it's the same for the 1 minus p term as well. So I can swap the product here for the sum of all of these terms. Now, if I'm thinking about the sum of 3 minus xi, this expression here, I've got in each sum that I'm adding up, I've got 3. None of those depend on I. So I can write this as 15 minus the sum of the x's. Okay, awesome. So with that in mind, we've got part B. And I want you guys to give part B a go. So in part B, we've been given a particular sample. We've been given x1 equals 1, x2 equals 3, x3 equals 2, x4 equals 2, and x5 equals 3. So we've been given this particular example. I would say, first of all, try and simplify LP a little bit so that it doesn't have any xi's anymore. It's just got numbers in. Okay, so simplify LP a little bit by plugging in these values of xi. And then for the p's that were given, calculate what L is. So I'm just like you to just populate a little table. We've got P 0.5, 0.6, 0.7, 0.8. We want to know what LP is. And then from those LPs, we want to try and take the one that's biggest as the one that's the maximum likelihood estimator, so the one that's most likely to be the correct value of P. So I'm going to give you a solid definitely 5 minutes to give that a go. Yeah, just crack on, give it a go. And when you know what the answer is, direct message me a potential candidate for the answer. When I've got a few of those through, we can start ourselves off. If you've got any questions, direct message me as well. If you're completely lost, direct message me. Yeah, I'm very open for communication at this point because it'll help me figure out whether I'm going too fast, too slow, or I'm boring, or yeah. Well, I am boring that much, so I don't care. Okay, so does anybody have a potential candidate for P, for the best choice of P? Yeah, so Lewis has made a suggestion there to everybody. Has anybody else got a different one from Lewis, or anybody agree with Lewis on P is equal to 0.5? Okay, so where I started from with this is just, first of all, doing the simplifying a little bit. So when I added up all of these, I got to 11. So I know that I can replace the sum here with 11. And then 15 minus 11 is 4. And the question is what's this constant? So if I've got 3 to choose from, if I'm picking out only one, there's going to be 3 ways of doing that. If I'm picking 3, there's going to be only one way of doing that. Picking 2, I'm back to 3 ways again. And one way of picking 3. So if I multiply all of these together, I'm going to have 3 raised to the power of 3. So my constant's going to be a 27. So I'm going to need to use this formula to find out the value of LP for each value of P. If I plug in my values of P, the biggest one is actually 0.7. And the reason for this is that basically the factors on the first one is smaller. It looks initially like it's bigger because you get 8.24 times 10 to the power of minus 4, and all of the rest to the power of minus 3, 2.51. Okay. Yeah, so it's called the maximum likelihood estimator. So that's why we're trying to pick the biggest one. I think it's kind of possibly an easy mistake to be making, is either misreading the powers when you've got terms expressed in those kind of terms and thinking, oh, eight's bigger than 4, eight's the one to go with, or alternatively thinking like, oh, so it's a maximum likelihood estimator, I've got to try and find the minimum value. But the clue is in the name, guys. Let's keep it to maximum likelihood estimator. So it's the biggest one, it's the 0.7 there. But it doesn't matter. I mean, if you got all of the way to all of the right answers there at the end, and then you just highlighted the wrong one, you're going to be scoring all but 1 point on this type of question. That's good enough in my book. That's good enough in my book. Okay. So the next question is about the confidence intervals. And if you were a bit early, you probably heard me waffling on about not having a good time talking about this question in previous classes. So fingers crossed to do a bit better. And I'm hoping I will on the basis that I've got a little bit more time and I don't need to try and rush it into 3 or 4 minutes at the end. So what's going on? I've been given a sample of size 10, so n is equal to 10. And the sample is written out in the question. There's 10 values there that you've been given. We've been told we know what the standard deviation of the underlying distribution is. It's 0.8. We don't know what the mean of the underlying distribution is. So we've got no idea what the mean of the underlying distribution is, but we do have these 10 values and we can calculate the mean of them. So we can calculate the sample mean, but we don't know what the underlying mean is. We've been asked to find a 95% confidence interval for the mean of the underlying distribution. So how I'd like to think about this is I'd like to think about the fact that I'm looking for an interval so that there's a 2.5% chance that we're lower than one end of this interval, 2.5% chance that mu is here, and a 2.5% chance that it's here. Okay. Now, in the middle of this confidence interval is going to be the sample mean, because that's really like the best guess that we could possibly have. So right slap bang in the middle here is going to be X bar sample mean. Okay. So what's the value of that? We can calculate that from the question. We've got those 10 values there. We can add them all up and divide by 10. And we should be able to get that that's 11.48. Okay, so in terms of finding a range which there's a 95% chance that that mu is in that range, what we need to do is we need to use some of the properties of that sample mean. So we know that the sample mean is normally distributed, and we know that the parameters are so we know that it's normally distributed around the actual mean mu, and we know that its variance relates to the sample size as well. So that fact is going to help us with what the ends of this interval should be. So we're going to be looking for an interval of a certain type. It's going to have the sample mean minus, and then a value z, and then the variance of the sample, so the standard deviation of the sample. I'm going to call that Z star in both cases. And what Z star is going to do is Z star is going to tell us, you know, how many standard deviations or like away, you know, how far away in terms of standard deviations we need to be from the mean in terms of the normal distribution with parameters 0 and 1, such that this interval is of the right size. So the Z star that we're looking for so if I stick it into the CDF of the normal distribution with parameters 0 and 1, so Z star in here, we should get that it's the 97.5th percentile in this particular case, because we want to be leaving 2.5% at this end. So we want to be going to 0.975. And it's easy to make a little mistake here in thinking, oh, it's the 95th percentile, so I need to put 0.95 here. And I have definitely done that at least once as an undergraduate, is put 0.95 here instead of 0.975, and then wondered where I'd gone wrong, and I'd put all, but that if I put 0.95 here, I'd have 5% at the top end of the interval and 5% at the bottom end of the interval. So it would be a 90% confidence interval, not a 95% confidence interval. So to sort of help us along those lines, the notation that Sarah Lees is using is, instead of a Z star, he is using Z1 minus alpha divided by 2, where alpha is what we need to be excluding, so the 5%, so 0.05 in this case. Yeah, and then that sort of gets us into a case here where we can't make that kind of slip up, because we've got 1 minus alpha minus 2 indexing our Z to sort of remind us what type of Z we're looking for, and then the expression here is exactly that, so 1 minus 0.05 divided by 2. Yep. So with that in mind, if I plug in all of those values that I know, I am going to end up with a confidence interval that looks like 11.48 minus Z1 minus 0.975 times 0.8, all divided by the square root of 10, and then 11.4, and then the positive rather than negative here. Okay, so in order to find the value of that Z, you're going to need to look that up in your normal distribution table. So what I'd like you to do with the final 3 minutes we've got together is have a think about what that value of Z would be in this particular case. Look it up in your normal distribution table if you've got one handy, and have a think about what, if anything, you would need to change to answer part B, so to make it into a 99% confidence interval instead. What would you need to change? Would you be changing sigma? Would you be changing n? Would you be changing x bar? Would you be changing z? And if you would be changing one of those things, in what way would you be changing it? And just give a quick go of modifying that variable as well. You've got about 2 minutes until our scheduled end time, but I will hang around for about 5 minutes afterwards just in case you want to ask anything. Feel free to just kind of work on that. Feel free to shout out any kind of answer that you've got in the chat. Feel free to direct message me if you've got a proposed answer. Even if you just thought, no, I'm afraid to say you've done that for the third time, it's still not clear the way that you explained that question. Just DM me that so that I know that I'm an idiot. Aside from that, have a really nice end to your week, and I'll see you in a fortnight's time. And that will be for our final tutorial, which is a really weird thought. So yeah, have a nice evening, everyone.
It sounds like somebody's having like a major kind of malfunction upstairs. It's like, I have no idea what he's doing to that baby, but it sounds horrendous. So in a minute or two, I'm just going to assume that the two of you that are still here have just like wandered away from your computers because it's like literally so boring when I'm teaching you. Which I assume that it's not that boring, but there's many more interesting things in life, and that you probably just got distracted by something going on in your homes. I think we might need to like just leave Sarah Lee's on his own in the room.